General rules. The system should only be used for purposes described in this operating instruction. The system should only be used by trained personnel. It is mandatory that users understand and know the content of the operating instruction handed over by Micafil. The user is responsible for maintaining the good condition of the plant. Prior to operating the LFH plant, its condition must be checked according to the operating instructions. Lifting of components should only be done using the foreseen lifting points. Caution should be taken when lifting heavy devices. The purpose of any safety device should not be altered, nor should they be removed. All labels and inscriptions on plant components must not be removed or altered. Power and earth cables must be properly connected to the transformer. During the operation of the plant, strong electromagnetic fields are present, which could affect the functioning of electronic equipment or even damage it. Special attention should be paid by people using heart pacemakers or other medical implants. Safety barriers with clear inscription should be installed at the area of the transformer under tension whenever a drying process is being carried out. All markings should be clear and adhere to the local safety rules. Connection of the oil heating system for oil spray must be done according to local regulations, oil spill protection, inscriptions, barriers, etc. During all work on the transformer, the operator has to make sure that the converter is turned off. It must be assured that no water can enter the installation. Control panels. Should it be necessary to open the control panel, the main switch must be switched off. All electrical maintenance work and interventions on the electrical equipment should only be done by licensed electricians. Altering of the general parameters and the fixed values should only be done in consultation with Micafil. Process parameter sets should only be elaborated by an experienced transformer drying specialist. All maintenance work should be done by qualified personnel. Pre-start physical connections. The completely assembled transformer, including bushings and tap changers, is placed in front of the vacuum and heating equipment. The following work has to be done before process start. Connect the power cables to the power supply. For high currents greater than 100 amperes, bolts instead of clamps should be used. Make sure that the bolts are properly tightened. Apply appropriate markings so that personnel do not accidentally get close to the transformer and its connections. The power cables should be connected between the converter and the high voltage bushings. For transformers with a high current rating, 2 cables have to be connected in parallel, 2 × 120 mm squared. The cables for the external voltage measuring can be connected to the high voltage bushings if the power cables will be extended or the transformer has an extremely low resistance. These external voltage measurements will then compensate for the resistance in the power cables. The low voltage windings should be short-circuited. The connection must be able to hold the nominal current of the LV side of the transformer. For high currents greater than 100 amperes, bolts instead of clamps should be used. Make sure that the bolts are properly tightened. Also, when drying an auto transformer, the LV side has to be short-circuited. If the transformer has a tertiary winding, this one is normally left open or not connected. Connect the grounding cable to the transformer tank. Connect the vacuum flange with the vacuum regulation valve to the transformer. Connect pressure probes 202 and 244, aeration valve 243, and vacuum regulation valve 241. Connect and secure the VZ406 together with the VZ475. Check if the powder P205 in the VZ406 needs to be changed. Cover the pressure probes with a plastic or similar type bag in order to protect the sensors from rain, snow, or dust. Ensure that the aeration valve can still operate and aerate the tank. Make sure that there are no leaks. Connect the flexible vacuum hoses to the vacuum flange. The oil circulation connection fittings have to be connected to the transformer, and the connection has to be free of leaks. Connect the temperature sensors for measuring the object temperatures, if applicable. Connect the signal cables to the oil treatment plant. Sensors on top of transformer. This is a brief overview of the sensor and valve system that is mounted on the top of the transformer.
What we have here is the valve, which is used to control the vacuum for the LFH. With this, we can control the vacuum through the use of this electronically controlled valve. The other thing we have is this valve right here can be is used to control the dry air. Other components that are very important here are the vacuum sensors. There's a Pirani, which is the fine vacuum sensor, and on the other side here is the Wicca, which is the coarse vacuum sensor. The Wicca's accuracy gauge is anywhere from 10 to 1000 millibar, while as the Pirani here is 0 to 10 millibar. With this unit here, we also have connections for thermocouple probes, which are installed in the transformer. The connections for those thermocouple probes are right here. You see the 4 probes. These probes are installed inside of the transformer. 2 are near the top and 2 are near the bottom of the core and coils. The other important thing in regards to this valve is the adapter flanges. Since these flanges are not our standard type of flange, you do need an adapter that goes from this style of bolt pattern to our standard bolt pattern. I think that's about it. Oh yeah, this is the same thing right here. This flange as well is an adapter flange, which goes from the European style of standard flange to one of our Canadian or American style of flanges. Very important to have these adapters though here and here in order to install the valve assembly onto the transformer. Okay, this is the motor drive for the valve, for the positioning valve. This right here is the actual valve that's being positioned. It can be moved in any degrees from 0, which is fully closed, to 90 degrees, which is fully open, and any degree therein by using the HMI controls down on the computer. On this valve as well, there is also a manual override that you can use to set this valve manually in case of loss of power. There's a switch on the back that you turn to manual and hold it there. When you do this on top of here, you take this indicator off and the shaft is actually keyed, so you can use an adjustable wrench to position the valve closed or open if in case of any power outage or anything like that and you need to control the valve. Okay. This valve here is used to control the dry air being injected into the machine for the heating cycle. This is the control for it. It's an actual coil. Unlike the previous valve, when there is loss of power, this valve closes. This is the control for it, the coil. This is the actual valve right here, and here is your connection for your dry air. Okay, these are the 4 probes that are installed in the transformer, the thermocouples. There's 4 of them, 1, 2, 3, and 4. These are installed in the top and bottom of the transformer winding to see what temperature is actually inside the transformer during the heating of it. This right here is a Pirani vacuum gauge. It's the fine vacuum gauge, so to speak. It is accurate between 0 and 10 millibar. On the back side of the valve assembly is the Wicca pressure gauge. This is the coarse vacuum sensor. It is accurate between 10 and 1000 millibar. In regards to the Pirani gauge, since it is a very sensitive instrument, it only goes between 0 and 10 millibar. You do need, while installing it, you do require to put an insulated gasket as well as an insulated clamp on it in order for it to function properly. And you will notice fluctuations in the vacuum readings while you're injecting current into the transformer. That's one telltale sign that it's not being insulated properly. This valve here in the middle is a manual aeration valve. It can also be used to aerate the transformer, but if you are going to use this valve, I do suggest to connect the dry air line to it. Here we have an adapter flange, which is used to go from a European style of flange to our American styles of flange. Very important to have this piece. Without this piece, you will not be able to connect the vacuum valve assembly to the transformer. This adapter flange works on this 4-inch gate valve, but it all depends on what kind of bolt hole pattern you do have on the transformer. For this one, as I mentioned before, it is on a 4-inch gate valve. Sometimes you'll be connecting to, say, a Qualitrol or some sort of a Ph.D. stack. You just need to be aware of what type of bolt hole pattern is on the transformer and what you require in order to attach the flange onto it as well. Okay. Another important connection to take into consideration is the vacuum connection. Again, this bolt hole pattern is not our standard bolt hole pattern, so make sure that you do have a flange that can bolt up to this pattern and also connect to it's usually a 4-inch vacuum hose as well, cam lock style of a fitting.
Overview. General function. With this plant, 3-phase and single-phase transformers can be dried. The winding of the transformers are heated with low-frequency current. Other parts inside of the transformer are heated with oil circulation or hot oil spray. The extraction of the water is being done by heating the windings with low-frequency current and by heating the insulation with oil circulation. Vacuum is applied to the transformer to extract the maximum amount of water. There is a measurement device for the specific water extraction installed in the oil treatment plant and incorporated in the control software. This device is called VZ406 and works together with the pump suction capacity measuring device called VZ475. Overview. Data input and process start. The transformer's data should be entered in the transformer data screen. It is recommended that these parameters are cross-checked before starting the process to ensure that the correct values are entered. Wrong input of values can lead to current levels that can damage the transformer. The data should be checked against the data plate of the transformer and any available technical information. The initial temperature of the transformer can be taken automatically from the temperature sensor, which is mounted inside the container. There is also the possibility to enter the temperature manually by clicking the checkbox. Then the actual temperature for the transformer can be entered, and this value will be used as the reference value for the transformer during the heating. It is essential that the correct value for the transformer temperature is used. In other cases, there is a risk for overheating the transformer. It is recommended to use temperature sensors on the drying object as a reference, since the temperature in the container can deviate from the temperature of the transformer. During the process, some of the inputs can be altered by the operator. For example, maximum current. Parameters that cannot be changed during the process are disabled. After entering and rechecking that all necessary information for the transformer has been entered, the data has to be confirmed by switching the switch on the right side of the screen to the green color. A startup of the system is only possible after confirming the data. Overview. Measuring. The measuring phase is measuring the initial resistance of the windings and assigning the starting temperature to the measured values. This resistance will then be used as a reference value for all temperature calculations throughout the entire process. When the transformer data has been entered and confirmed, and all parameters have been entered, the process can be started. This is done by clicking on Measuring in the phase screen. Prior to this, make sure that the converter as well as the UPS are switched on at the converter panel. The converter errors are cleared and all components are in automatic mode. Resetting of the alarms in the converter can be made in the lower part of this screen. There is a button that will send the signal to the converter to clear the alarms. Alarms not related to the converter will be reset from the alarm screen. This measuring phase should never be started after heating up the transformer. If this is done, then the temperature will not be correct and the transformer will be overheated, which may destroy the transformer. After switching off the process, it always needs to be restarted with the warm restart function, which keeps the initial resistance values and just remeasures the temperature of the transformer. It is extremely important that the warm restart is made, and not a new measurement. If the values from the initial resistance measurements are lost, the measurement must be made and the temperature of the windings must be re-entered manually. Entering a wrong temperature value can result in overheating the transformer. Also, prior to the restart, you need to make sure that all the starting input data are still correct, the entering of the data and checking is confirmed, the converter errors are cleared, and all components are in automatic mode. Overview. Heating 1. The transformer is heated by means of LF current in combination with oil circulation or hot oil spray to the first temperature set point. Once reached, the set point of the converter will stabilize the temperature inside the transformer by means of stopping and starting the current injection. If a combination with oil spray is selected, vacuum will be applied at the same time. The first temperature step is kept constant for a certain time, Z3, in order that a uniform temperature distribution in the insulation can take place. A few degrees, DT1 normally 5 degrees, before reaching T1, the system will measure the temperature in the HV winding and calculate the temperature in the LV winding. If the temperature in the HV winding is much lower than the average winding, the converter will heat the HV winding separately if this is selected on the start screen. The aim of the stabilization phase is to remove as much water from the insulation as possible at a relatively low temperature. In order to guarantee optimized drying results, the transformer tank will be evacuated during a certain time, Z23, without heating. And then the winding will be intermittently heated again with LFH current. This assures a better drying quality and reduces the overall drying time. Flashover is prevented through partially raising the vacuum in the transformer tank with air between each evacuation. After reaching the time Z3, the process will go on with the next phase. Overview. Evacuation. The transformer is heated to the next temperature set point. Through vacuum stabilization, a flashover, according to the Paschen law, is prevented. Should for some reason the vacuum fall below P20, the LFH heating stops immediately. After reaching T11 and the temperature for the HV winding has been brought near the average temperature, the process will be switched on to the fine vacuum 1. When oil circulation is selected, the oil should be drained out of the transformer during this process step. Overview. Fine vacuum 1. In order to guarantee optimized drying results, the winding temperature will be intermittently heated with LFH current during a certain period of the whole fine vacuum 1 time, Z25. This assures a better drying quality and reduces the overall drying time. Flashovers are prevented through partially raising the vacuum in the transformer tank with air. After reaching Z25, the process will be switched on to the fine vacuum 2. When oil spray is selected, the oil spray should be stopped at the end of this process step and the oil drained to the storage tanks. Overview. Fine vacuum 2. The transformer will now be heated to the final temperature set point. After reaching T25, the winding temperature will be intermittently heated with LFH current. Following that, the pressure will be lowered until reaching P21 and UP230 WSA, specific water extraction. These two parameters will allow the process to stop. Alarms and warnings. There are certain alarms that are coming from the converter and other alarms that are coming from the rest of the plant. The converter alarms must be reset in the phase control screen, while the alarms from the rest of the plant should be reset in the alarm screen. There is a similar screen for warnings. Most alarms do not need to be reset. When the situation that has created the alarm has been solved, the alarm is reset, but it still remains green, waiting for the acknowledgement from the operator. The process will go on in the meantime. Summary. The main functionality of the process plant is shown in the main process picture. In this screen, temperature sensors can be deselected if they are not connected. There is an indication if there is an alarm in the oil treatment plant. The oil temperature used as a reference for the converter to compare with the winding temperature is the average temperature. The average temperature is based on which sensors are selected. If neither of T8 and T9 is selected, then T9 will be used as the average temperature. Temperature sensors T1 through T4 are only used as information for the operator and do not affect the process. If the temperature sensors are connected and are facing some problem, an alarm will be triggered. This alarm can be deactivated by unchecking the checkbox for each temperature sensor. The average temperature value is updated along the process, but the HV and the LV values are only updated when the HV measurement has taken place. Between these measurements, these values are not changed. Parameter descriptions. There is a set of parameters that the operator can adjust to change the operation of the plant. The parameters are divided into 5 groups: 230, Wind 1, Common, VZ406, and Fixed. The 230 parameters and the wind parameters are the only ones the operator can change and should adjust for each process and maybe also during the process. The common ones should remain very much the same from process to process, and the fixed parameters cannot be changed by the operator. In the parameter list, there is a minimum value and a maximum value, indicating within which range that the value is allowed or expected. These limits are meant to prevent the operator from accidentally entering the wrong value. The maximum and minimum limit values can be changed by clicking on the actual values. In order to do this, an access level 4 or 5 is needed. The parameters are described in order of appearance. Starting the process. There are several different ways of starting the process. The first is the normal process start. That means that the transformer has not been running and is at an ambient temperature, or the previous resistance reference values have been lost and a new measurement needs to be performed. A warm restart bypasses the first stage that correlates the resistance of the windings with their temperatures. It goes directly to the heating stage. Data entry steps. Turn on the main power supply on the control cabinet. Turn on the UPS and make sure that the emergency stop is not activated. Close the cabinet doors. Make sure that all components, such as valves and pumps, are set to automatic. Enter the transformer data into the 230 input screen and compare it to the nameplate of the transformer and the technical data sheet. These data consist of the following: customer reference information, which contains the identifier for the transformer; insulation weight, as accurately as possible as it is used by the VZ406 to calculate the final water extraction rate; transformer capacity value in MVA that is used to calculate the nominal current of the transformer; transformer voltages for the high voltage and low voltage values in kilovolts, which are also used to calculate the nominal current; copper losses of short circuit test. The load losses, if they are known, should be entered as kilowatts. Relative ohm short circuit voltage, μR, can be entered as a percent so that the copper losses can be calculated. Maximum drying current for the average voltage heating is the absolutely maximum current that will not be exceeded by the LFH plant, even if the CF factor is asking for more current. It is used as a design safety factor to prevent damage to the transformer. The value is entered as amperes. Maximum drying current for the high voltage heating is the absolutely maximum current that will not be exceeded by the LFH plant, even if the CF factor is asking for more current. It is used as a design safety factor to prevent damage to the transformer. The value is entered as amperes. Material composition for high and low voltage windings is important to know in order to calculate the resistance and temperature relationships. Either copper or aluminum is possible, and they can be different in the high voltage and low voltage windings. Connection of the transformer HV-LV has to be known in order to calculate the nominal currents. The choices are a star connection, that is a common ground, or a delta connection, that is a floating ground. Number of phases. The system is designed to dry either single or three-phase transformers. If a single-phase transformer is connected, it has to be connected to the top two connections, the RS. Nominal current connected winding is a calculated value and is not entered by the operator. Check to enable minimum vacuum control. Check this box if you want to limit the minimum vacuum value. This may be necessary if the transformer cannot withstand a substantial force resulting from the internal vacuum. Enter an appropriate value. Ambient temperature as reference. If the transformer is not at ambient temperature due to a previous heat-up, then a different reference temperature should be entered and used for the reference measurement stage. HV heating on. Activating this feature allows one to heat the HV winding separately. If it is not activated, then the system will use average heating. HV measurement and heating in the heating stage. If this is not selected, then no HV measurements will be made during the measurement and during the heating stages. The HV measurements would then be made in the fine vacuum stages. HV heating in the stabilization stage. If HV heating is preferred in the stabilization phase, the HV measurement will be done after each heating break. The recommendation is to use all HV heating modes only when there is a big difference in current density between the windings, or the design will generate an asymmetric heating. The HV measurement takes some time, and the oil circulation system normally ensures that the temperature is relatively evenly distributed. Converter connected to LV windings. If the converter is connected to the LV winding, all data is entered as normal, but this box is checked, and the nominal current will be recalculated and all measurements will be correct. If not, the HV data has to be taken from the LV and so on, and the LV and HV data will be switched. When connected to the LV winding, the HV winding has to be shortened. The connection procedure is very rare and should only be used when it is not possible to connect to the HV winding, or the current density of the LV winding is much lower than the HV winding. In all normal cases, the HV winding should be connected since it can be difficult to reach nominal current on the LV winding. Select oil spray process. If the LFH process is combined with an oil spray process, this box must be checked. Then, different parameters will be considered in the process. It is of utmost importance that these data are correct since the converter will calculate the current and voltage based on this information. Wrong data can result in damage to the transformer. After these data have been confirmed, then the virtual switch is set to the green position. Measurement step. This step should not be carried out if the transformer has been previously heated up. If this step is carried out on a transformer that is still warm from heating, then the temperature setting will not be correct, and that could lead to overheating that could destroy the transformer. If the LFH is being run in a mobile environment, then the semi-automatic mode should be selected, and the process will stay in each stage, measuring, heating, and fine vacuum, and the operator has to manually transit the process to the next stage. There are some actions and decisions that need to be made by the operator, and the interaction with the oil plant needs manual actions where it can be of benefit that the plant does not automatically transit between the stages. On a transformer that is at ambient temperature, start the process by clicking on Measuring, which is located on the 230 process screen. The control system checks the input data and the process will automatically start in the measuring step. If some conditions are not fulfilled, the process will not be possible to start. Recheck all of the parameters, entered corrected transformer values, and correct any wiring errors in this case. When the measuring button turns green, the following actions are carried out by the control system. The proper voltage is calculated and set. The converter gets the command for the average voltage reference measurement. The average resistance is measured in the converter and is stored in the PLC together with the reference temperature for the measurement. If the HV measurement has been selected, the PLC will send a command to the converter to measure the resistance in the high voltage winding. This is done at the frequency set in value F201. The measured resistance in the HV winding is set to the PLC and is stored together with the calculated low voltage resistance. These values, together with the average voltage values, are used as the reference for the entire process. The following values are checked or calculated. The variation of the resistance distribution over all phases are checked and calculated. The deviation of resistance measures in sequence are measured and calculated. The maximum and minimum currents needed for the process are determined. The maximum power needed for the process is determined. The currents below the maximum for the average and high voltages are set. If all the measurements are correct and meet specification, then the Heating 1 sequence will be allowed. Heating 1 step. When the virtual heating button is pressed, the control system carries out a number of actions, some of which are concurrent and some of which are sequential. The control system regulates the temperature rise according to the constraints entered by the operator. The heating frequency used is taken from the F200 parameter data field and is usually about 1 Hz. If selected, high voltage measurements are taken. Various timers and condition set points will activate relevant actions as the Heating 1 process step proceeds. The process continues until the set point temperature T1 is reached and the timing set point conditions for Z3 and Z4 are met. If all other system parameters are nominal, then the operator can proceed to the evacuation step. Evaporation step. The operator can initiate the evaporation step by pressing the virtual button on the control screen called Evaporation. At that point, if the transformer was filled with heated recirculating oil, the oil is pumped out of the transformer. If the heated oil is being sprayed and circulated, then that part of the process continues on into the fine vacuum 1 stage. The main vacuum pumping system and the booster pump are turned on. The control system regulates the vacuum valve 241 and the aeration valve 243 to meet the pressure set point defined by parameter P20. The low-frequency heating temperature rise is controlled and regulated according to the set point parameters. The CF factor cannot exceed the maximum set point value for that parameter, even if the temperature rise requirements are not being met. At a conditional point in the process, the temperature of the high-voltage windings are taken, and the temperature of the low-voltage windings are calculated. Depending on the temperature values, the heating frequency can be changed by the system in order to meet the process set point conditions. When the temperature reaches the value defined by the temperature parameter T11 and the pressure reaches the pressure parameter P20, then the process can be manually advanced to the next step, that is, the Fine Vacuum 1 step. Fine Vacuum 1 step. The operator presses the virtual button Fine Vacuum 1 on the control screen to start this step in the process. The temperature rise starts according to the set point parameter DTZ40S, using the heating frequency defined by the parameter F200. The CF value cannot exceed its maximum set point safety setting. A number of process timers are started, which collectively govern the duration of this step. When the time defined by the set point parameter Z25 has elapsed and the temperature T11 has been reached, then the process can advance to the final Fine Vacuum 2 step. Fine Vacuum 2 step. The operator presses the virtual button Fine Vacuum 2 to start this final step of the process. If the oil spray process has been employed, then the operator should press the virtual oil drainage button located on the same screen. This stops the low-frequency heating while the oil is being drained. After the draining is complete, the operator presses the oil drainage one more time, and that initiates the stabilization period. The vacuum continues to increase, and when the pressure has fallen below the value specified by P21, the timer Z20 has elapsed, and the specific water extraction level has been reached in subsequent readings, then the process has achieved its objectives, and the operator can press the off button, which will lead to the manual aeration of the transformer. Theory of the VZ406EL instrument. The purpose of this instrument is to provide the data necessary to calculate the amount of water that has been extracted from the transformer insulation during the entire low-frequency heating process. The instrument provides the suction capacity of the vacuum pumping system in cubic meters per hour and the concentration of water vapor in grams per cubic meter as a function of time. Knowing these values allows one to calculate the total weight of water removed from the transformer. Using simple dimensional analysis, you can see that the product of the concentration of water in grams per cubic meter times the pumping rate in cubic meters per hour times the number of hours yields the number of grams of water extracted from the system. In order to be able to calculate the suction or pumping capacity of any given pumping system used for a mobile processing session, it is necessary to construct a calibration curve that relates the measured pressure in the VZ406 to a pumping capacity in cubic meters per second. To create that calibration curve, a series of 5 valves with known leakage rates are individually opened, one at a time, and the steady-state pressure is measured for each one. This allows the computer to create a calibration curve over the expected range of values from 1 to 10 millibars. Knowing the pressure will then tell you the pumping rate at that point. A diagrammatic view of the VZ406 is shown here. It has a measuring chamber that contains a closable chamber within it that contains phosphorus pentoxide. This material is corrosive and toxic. Consequently, gloves and eye protection are mandatory. Be aware of the proper cleanup procedure in the event that any material is spilled. Valves 1 and 2 and the linear lifting motor are controlled by the computer. The pressure sensor can be read remotely by the computer. The VZ406 passes a steady mixture of water vapor and air through it at the flushing stage. Then valve is closed, and then the chamber equilibrates to the final pressure that consists of the remaining air and the partial pressure of the water vapor in the effluent. At the time of measurement, the unit is sealed and the phosphorus pentoxide chamber opens and absorbs the water. The pressure gauge falls proportionately to the loss in water vapor pressure, and the computer is then able to calculate the concentration of water in grams per cubic meter at that point in time. The phosphorus pentoxide chamber closes, and the 2 valves remain closed, and the system is tested to ensure that there are no leaks. This shows the sequence of steps involved in taking on a measurement. The integration of these points over time results in the amount of water extracted from the process. VZ475 Suction Capacity Measurement. The VZ475 system is used to generate a calibration curve that relates the suction capacity of the vacuum system in cubic meters per hour to the pressure while the vacuum system is running. This value is necessary to calculate the amount of water removed from the system through the duration of the LFH process.
The VZ475 is connected via a split box with 5 cables which are connected to the magnetic valves with 5 separate cables. From the split box One cable goes directly and is connected to the backside of the control panel in the converter trailer. Each valve is then individually controlled from the control system and opens in a sequence that is predetermined by the program. Each valve has a certain leakage rate. This leakage rate is generating a leakage to the vacuum pumps. By this vacuum pump leakage and the final pressure, we can determine the pump capacity. This pump capacity is then a basic for the pressure readings used for the VZ406, which is in the next stage measuring the water extraction rate. This is a help that should be used for an unknown vacuum pump that has never been used before, or if it's a long time between the readings taken. Approximately 6 months between the readings is a rule of thumb. If for some reason the system is not working, the measurement can be entered manually into the system. What we see here now is a VZ475. It has a vacuum connection at the bottom, and to this split board there are 5 valves connected, each with an individually calibrated leakage valve. The leakage valve you can see here on the side of the magnetic valve. This valve has a unique characteristic and is factory calibrated. Handle this with care because this is very sensitive. The second, third, fourth and fifth valve can be seen. This is the calibrated part of the valve with the silencer, which is generating the calibrated leakage rate. This black here is a plastic part which connects the silencer to the magnetic valve, and that's where you have the sensitivity. Handle with care. When mounting and dismounting the valves, disconnect the caps from the valves and reconnect them again. Make sure each valve has its corresponding cap. Valve 3 in this case has cap number 3. The whole VZ475 device should be connected to the vacuum line. That is done by this quick coupling connection. Unscrew it. And open. Then the vacuum line can be removed. This is a split box with the 5 inputs, 1, 2, 3, 4, 5, where a cable goes to the magnetic valves on the VZ475. The 6th cable is a main cable going to the control cabinet. The vacuum connection for the VZ475 should be after the booster, the roots pump, and directly connected to the main vacuum line. This is the VZ406. It's a water measuring device used for measuring how much water is coming out from the transformer. Its purpose is to be able to determine the total amount of volume extracted and the momentarily extraction rate. It has a vacuum chamber inside from which moisture is reduced, and it's reduced through a powder called phosphor pentoxide contained in a container. This container is located under the device here. You can exchange the powder by opening the lever, take out the glass, and exchange the powder. When the powder is exchanged, put the glass in again and pull down the lever. Notice that very little force has to be used when operating the lever. If extensive force is needed, you'll probably have vacuum in the chamber, and there is a major risk that you break the glass. When exchanging the powder, the lever should be raised using gentle force up, take out the glass, and exchange the powder. When the powder has been exchanged, put the glass back in, slide it into position, and gently lower the lever. The powder has normally a white color. When it gets moisturized and old, it changes color to purple. This can be seen using the mirror and watching the color change of the powder. This should be done on a daily basis during operation and before every operation. On the back side of the VSAD 406 you have the vacuum connections and the electrical connections. The vacuum connections has to be connected over the root pump. The upper connection should be on the suction side of the root pump, and the lower connection should be on the pressure side of the root pump. The electrical connection goes directly to the control panel in the converter trailer. There are two electrical connections. One is for the magnetic valves and the motor, and the second one is for the pressure sensor inside the VSAD 406. The upper vacuum connection should be connected to a point between the root pump and the transformer, that is on the low pressure side of the vacuum pump. The lower vacuum connection should be connected between the root pump and the vacuum pumps, that is on the pressure side of the root pump.
Effect of water in transformers. Transformers are the heart of any electrical distribution system and are expensive capital items. If they fail unexpectedly, then the impact on customer service as well as system restoration can be very expensive. Transformers require several internal electrical insulation strategies to function properly. Transformer oil serves to facilitate cooling, and it also provides a high dielectric medium to prevent high voltage arcing within the transformer. The other principal insulation medium is a type of cellulose paper. A large transformer can contain many tons of this material, along with thousands of liters of transformer oil. If the internal electrical insulation systems break down, then the transformer life can be shortened significantly, and that has negative service and cost implications. A dry transformer can last decades longer than one with unacceptable moisture leaks. In the simplest of terms, water within a transformer needs to be minimized if the service provider wants to maximize service and equipment life. The water within a transformer equilibrates itself between the oil and the insulation paper, with 99% of the moisture residing in the paper. As an example, a 400 MVA transformer with 15 tons of cellulose insulation and 60 tons of oil, with an average of 3% water in the cellulose, will equilibrate to 450 liters of water in the cellulose and 0.6 liters of water in the oil. Low-frequency heating concept. After working through the physics of drying, one is left with the fact that temperature is the key parameter to control. Too high a temperature can destroy the transformer. Too low a temperature, and the efficiency and effectiveness become so slow as to be useless. The heating strategy needs to be able to implement a number of constraints to be effective and practical. As this process is frequently a mobile one, there are more constraints to provide the effective heating required to reach the needed drying temperature. As the transformer may not contain oil, high voltages cannot be applied to the transformer to generate the required current in the windings to produce the heat necessary to dry. The transformer needs to act as a transformer to induce current flow in the low-voltage windings to facilitate the heating process. The low-frequency heating approach allows one to get the necessary current flow in the high-voltage windings with less than 1% of the voltage that would be required at the nominal frequency of 60 Hz. Even at a low frequency, current flow is induced in the low-voltage windings, thus producing heat for the drying process. With a voltage in the range of hundreds of volts rather than thousands of volts, arcing within the transformer becomes non-existent. Mobile power is capable of supplying the electrical requirements of the low-frequency plant running under the constraints mentioned. In addition to the heating of the windings, vacuum is used to remove the water as it is driven from the cellulose insulation. A heated oil spray has a supporting function to heat insulation that is not in contact with the metal windings. A typical configuration of a low-frequency heating plant is shown here. As you can see, the low-voltage side is shorted out, and the LFH converter is connected to the high-voltage side of the transformer. A vacuum system is also connected to the transformer, as well as an oil heating and recirculation system. The moisture content in the vacuum stream is measured to calculate the total amount of water removed from the transformer. If only a DC voltage was applied to the high-voltage windings, then no induced current would flow in the low-voltage windings. Even frequencies of less than 1 Hz will induce current flow and facilitate the heating process. The working principle of low-frequency heating drying can be explained in the relationships shown here. The goal is to get sufficient current flow through the high-voltage windings without having to use high voltage. To do this, the short-circuit impedance Zk needs to approach the short-circuit effective resistance Rk. Zk is derived from two components, Xk and Rk. As we can see, the relative reactance Xk is a function of the inductance of the transformer, and that is fixed by design. We can also see that Xk is directly proportional to the applied frequency. The frequency is a variable that we can control and that forms the basis of the low-frequency heating concept. Therefore, at low frequencies, the impedance of the transformer approaches the effective short-circuit resistance. This allows the rated current to flow through the high-voltage winding at less than 1% of the voltage required at 60 Hz. The windings are heated, no arcing occurs, and current is induced in the low-voltage windings. The ABB system is capable of determining the temperature of the windings by determining the relationship between winding temperature and its resistance. This is not a trivial capability and helps to ensure that safe winding temperatures are not exceeded. The choice of frequency will determine whether or not both the HV and LV windings are heated, or only the high-voltage winding. As you can see, at 1 Hz, both windings are heated, but at 0.01 Hz, only the HV winding is heated. That frequency is too low to induce a current in the LV windings. Also, you can see the relationship between the HV, LV, and average temperatures in a typical process setting. Here are the input and output values for the converter. The DC link and the IGBT switch properties show what the LFH is capable of doing. The LFH cycle. There are 2 LFH cycles that can be selected from the menu bar. One LFH process involves an empty transformer where heated oil is sprayed into the transformer and recirculated. The oil heats part of the insulation that may not be in direct contact with the windings. The second process involves a transformer that is filled with oil for the initial heating steps of the process, but which is removed in the evaporation stage. Each one of the 2 processes have the same number of key steps. They differ in timing of the oil removal from the transformer. For the oil circulation process, the oil is removed at the beginning of the evaporation step, as shown here. For the oil spray process, it is removed at the end of the fine vacuum 1 step. The first step for a new and cold transformer is the measuring step. This is followed by the main heating step called Heat 1. During the first 2 stages, no vacuum is applied to the transformer. At the evaporation step, the vacuum is applied to the system along with continued heating. The windings are heated through the interaction of 2 parameters. One is the current factor, or CF value, and the other is the frequency. The LFH plant can vary the frequency from 6 Hz down to 0.001 Hz. The latter is commonly stated in millihertz, with the lowest value being 1 millihertz. At the end of the frequency range, heating of the low-voltage windings takes place because of the AC inductive effect. At the low-frequency end, only the high-voltage winding takes place as the system approaches the behavior of a DC heated winding. The frequency cycles between step points designed to heat only the high-voltage winding and then both windings. The current factor has a maximum permitted value for the Heat 1 step and a maximum value for the remainder of the process steps. The current factor is controlled by the computer and is adjusted to meet the temperature rise requirements. The computer cannot exceed the current factor maximum set point values regardless of the heating outcome. The temperature of both the HV and LV windings are computed from the relationship derived in the measurement step between the resistances of the windings and their temperatures. An average temperature of all the windings for all of the HV and LV phase windings is also computed. You can see the temperature relationship for the process throughout the various steps. The temperature reaches a maximum value in each step as determined by the set points T1, T11, and T25. As you can see, these values are the average of the low and high voltage winding temperatures. The current factor is regulated on an updating schedule of 2-minute periods. The computer measures the rate of temperature rise and adjusts the CF to meet the set point requirements. As previously stated, the CF value cannot exceed the maximum set point value regardless of the needs of the heating algorithm. Shown here are some of the key parameters that control the heating cycles. Control system. The highlights of the control system are shown here. The main controller is connected to a laptop PC running a Windows operating system. When the system boots up on the laptop, one is presented with the startup page that has the serial number of the unit and the supplier's name at the top. One should ensure that all of the directories contain files. If they do not, the system may not work properly. The operator must log into the system by means of a username and password. There are a number of security levels, and most client users will have a Level 3 access code. Levels 4 and 5 are reserved for programming changes and are beyond the scope of the normal user. Before the processing can take place, certain critical information about the transformer being processed must be entered into the system. The first 3 lines just contain identifying information. The insulation weight is an important number and must be entered as accurately as possible. The insulation weight is used by the process to calculate the amount of water lost during processing. The remaining values are also used in the process, and any error in any entry may result in damage to the transformer. These values must be independently and carefully checked by a second person. When doing the checking, assume that there is an error until you prove to yourself that they are correct. Remember that windings can be made from either copper or aluminum. A wrong entry in this column will invalidate the relationship between winding temperature and winding resistance. This could cause damage to the transformer during the heating steps of the process. Also, there are different choices for the grounding and whether or not the transformer is 3-phase or single-phase. When all of the entry values have been checked and are correct, use the mouse to click on the virtual switch to confirm the entries. The operator can follow the progress of the LFH drawing by accessing a number of available screens. On this screen, the operator can confirm that the source power is connected, see what activities are occurring, follow key process parameters, as well as see what voltage and current is being fed to the transformer. This is an important screen, as it displays the resistance measurements taken during the measurement step. These values are used to relate the resistance to the temperature of the windings at any point in time during the process. The status of the VZ406 water measuring system and the VZ475 suction calibration can be checked on this screen page. The heating cycle values can be followed and viewed in real time on this screen. One can choose which process variables to trend. Click on the virtual button to make green to turn on. You can also see the respective values for each of the parameters. There are a series of screens which groups process variables, such as the timer variables and the trend variables screen, that plot the values of variables of interest are a function of time. Of course, there are event logs, warning logs, and alarm logs. The operator needs to know the significance of each of these and what action needs to be taken and when. Overview. This section highlights a live interactive teaching session given by Martin Carrison of ABB to Hydro One technical staff. 2 LFH units were being commissioned, and each one was used in parts of this 2-day teaching session.
We are here now at the startup, and starting the computer, you will have an icon on the desktop which says the product number. You double click that one and the system starts up. You will then have your startup screen. Important to notice if all the databases have some records, or if you see any errors out here. If you do, then you might have an issue to get all the recordings and so on properly done for the... Click anywhere, you come to the first page showing the transformer with its temperatures. These are actually the calculated temperatures and not the temperature sensors which we have installed. You have a schematic picture of the vacuum line to the vacuum regulation valve mounted on top of the transformer. You have the aeration valve for letting the dry air inlet to the system, and these two are automatically controlling the pressure level inside the transformer. We now have the coarse pressure in the transformer at 49 millibar, and since we are at this pressure range, the Pirani measurement sensor is showing a little bit different value. The rest is the root pump schematic, not controlled from here, and as well the main vacuum pump. Additional, there is possibility to install 2 temperature sensor for the oil circulation system. They are not installed, and we are not using them for any other purpose since we have not selected that process. 4 temperature sensors are installed inside the transformer. You select the sensors that you have installed, and this selection is for alarm purpose. If you have a break on the cable, you will then have an alarm if you have checked the checkbox. If you uncheck the checkbox, that means that only these 3 sensors are controlled. Now this alarm is only for checking if the sensor is broken or not broken. What's important to do, the first thing that you do is to log in. You do it up in the left corner. Click on it and enter your login name. Every login person has a unique name and unique password. Type your name, your password, enter, and then OK. Login was successful. Number here is changed from 0 to your login level, 3, 4, or 5. Normal login level is 3. So, after this, we go to the hand page, click on this one and you will have the transformer parameter data. This is the only input that you really have to do uniquely for each process. This is a unique parameters for unique parameter for each transformer. The first 3 lines are only reference numbers for you to know which transformer you're working with. Then it comes insulation weight. That's the estimated insulation weight of the transformer. It's used for measuring the end moisture extraction.
That's one you guess?
You make a good estimate for that, yes. If you don't have the exact data for it. Then comes the transformer capacity, MVA, found on the data sheet. You have the kilovolt ratings for the high voltage and the low voltage windings. Here it's important to take the right kilovolt according to the tap changer position. You should have as long winding as possible. And in this case, where we have a 2-winding secondary side, you should try to have the equal voltage range of both windings. Next, we're coming to the copper losses or short circuit resistance losses during short circuit test. This can be difficult to find, but a good estimate is to have 0.6% or 0.5% if you don't know it for power transformers of the rated power. If you put 10 tons, then you will have a better reading, so it's better to have a lower value than a higher value. What you do is that you go to this number, you click on it, you enter your values. Now it's 140 MVA, let's say it's 150 MVA, and you click and enter. Value is changed. Go back to our 140 MVA. That's all coming off from the transformer data sheet. Then, when we have entered these values correctly up here, we will come down to our maximum drying current for the heating. This is a safety factor. I will show later a little bit what's happening with the current factor and things like that. But this is for you to have really make sure that this factor, this value, we are never exceeding. The nominal current for this transformer is 320 amps. Let's say that we want to dry at about 50% of the nominal current. That's 150 amps, 160 amps. But if we make a mistake or anything, we never want to exceed 300 amps. Let's say so. You enter 300. And there you have 2 options for average heating when you're heating both high voltage and low voltage winding. You have an option to take only for the high voltage winding as well when you're heating only one side of the transformer. The maximum, yes.
Full winding.
The full winding. You can be a little bit conservative here. You don't have any oil cooling. You don't have any cooling effect at all. Still, this is only a safety factor.
Right.
So take 80-90% out of the maximum that you can expect. Important is to select the winding material, if it's copper or aluminum. Normally you're always working with copper, but you will have aluminum cases. If this is wrong, you will have a wrong temperature calculation in the heating up. You're coming to the transformer connection. You have 2 options, either star and zigzag, or you have a delta. You simply click on it and it changes. And this is then for high voltage side and also for the low voltage side. Do the same. Also information from the transformer data sheet. The last input from the transformer data sheet is the number of phases. If it's a single phase or a 3-phase transformer, you click, changes to a single phase, you click again, you can go for direct current heating, very seldom used, and in this case we have 3-phase. The nominal current for the transformer is calculated, check that again towards the data sheet, that this is correctly calculated. That's basically all information from the transformer data sheet. Now comes another few options you have. You can limit the vacuum in the transformer if the transformer tank does not take full vacuum. Then you check this box, and you have a parameter for that. That means that you can go down maybe to 500 millibar, maybe 700 millibar or something.
Where do you set that?
That comes on a parameter on this page here later.
Okay.
The initial temperature of the transformer can be visualized. At the moment we have four sensors which are attached to the transformer. You can simply take an average out of these values. Let's say it is approximately 22 degrees. Or you can take the ambient temperature. There is a temperature sensor inside the trailer. This is the ambient.
Is that going to be 85 degrees?
That's normally going to be 85 degrees here then.
Yeah. That's our starting point.
After oil circulation. So in 99% of the cases you will take this value and you will check it against these temperature sensors. You will have 87, 83, 84, 85,
Okay.
85.
Yep.
So we take this, make an estimate 22 degrees. We enter our 22 degrees into here and we leave that one open. There you really take the average, because if you check it you take the ambient temperature. I will make the change so it disappears, the one that you cannot select. Because when you check it you will use this value, then this one will disappear. You will not see it. It will be invisible, because you don't want to mix it up. Because if you come into a cold transformer and if you don't have the temperature sensor inside, then you start with ambient. Let's say it's been standing outside for weeks and you have not done anything, so
Wouldn't it be the same?
no, I will make that change, because I was confused myself yesterday and I have made a program change for it, but I have not implemented it here. Because this has to be clear which one is used, and that's why I wanted to have this value invisible when it is not applied. So, but I will make that for sure. Okay, the next option you will have is to perform a high voltage measurement, high voltage heating. That is to heat only one side of the transformer, and that is the winding you're connected to, which is a high voltage winding. I'm discussing in singular, but of course you're talking about all three windings. Then you will have two other high voltage measurement options, and that is for high voltage measurement and heating in the heating phase. And you have the high voltage heating in stabilization phase. Check both of them, and then you have the option to uncheck it later if you need to. The last two is if you're connected to the low voltage winding. Extremely rarely the case for power transformers, but you have the option to, instead of connecting to the high voltage side, you can connect to the low voltage side and short circuit the high voltage side. The problem you will face is that you don't have current enough to feed it.
Output current from the machine.
Output current from the machine. We are limited to
So the heat
500,
would be very, very slow.
close to non-existing.
Yeah, because of the capacity
If
of
you-
the low voltage side.
Yeah, because here we have a nominal current of 3000 amps, I think, on the low voltage, and we can supply 500, 600 amps.
Yeah.
So it's a fraction of. If you have a very small voltage difference between the high and low voltage side, and you know that you have a high current density on the low voltage side, so that one will heat up. Sorry, if you have a high current density on the high voltage side, so that one will heat extremely much faster than the low voltage.
Okay. Yeah.
The last box is when you have oil spray sensors connected. You will most of the time have it, and then you also will need the temperature sensor on the first page connected here. Oil spray. This one will make sure that we are not. It is a function for heating the transformer uniform with the oil temperature. Because if we are heating the transformer faster than the oil is heating the transformer, then we are just wasting energy.
Right.
So it is a little bit, he is kind of matching the transformer temperature to the oil circulation temperature. That is generally when you start from 20 degrees transformer heating up, and if you're heating up the transformer faster than you're heating up the oil, for example, then you're heating up the oil through the LFH, and that is a waste of energy. When you're done with all the data here, you confirm the entries by clicking this one, saying, okay, the entries are good. I'm satisfied. Normally one guy should enter the data, a second guy should check it. The second guy is then confirming this. And I emphasize once again, the initial temperature is crucial for the whole system to run at the proper temperature readings. That's what we are matching the resistance reading for the initial measurement to. Yeah. We have a set of parameters. There are general ones which are controlling. That is up here next to the traffic light, between the traffic light and the watch. And in here there are 5 pages. There are a general one for the process, the specific one for the current control. There are common ones, and there are ones for the suction capacity measurement. That's the VZ406 connected to vacuum pump stand. And there are fixed parameters which you cannot change. They are there for your information to see what is going on, what are the limits. One example is the minimum pressure for heating, that is called P920, safety pressure to switch off LFH heating command. That is set to 25 millibar, and that you cannot change. That is to avoid flashover scenarios. Can go lower than that and heat. LFH will not start. Here you can save by clicking on the open button. You can select something that you have saved before. We'll set up a few of these parameters for you to have as a standard batch. So then you match your 100 MVA transformer. Okay, I take a 100 MVA recipe. 200 MVA, take the 200 MVA. So what we have now is that we have set the current factors. So we are heating at minimum 20% of nominal current. We are heating at maximum 50% of nominal current. We have the frequency. We are nominally heating at 1 Hertz. We have an updating time of the temperature rise of 2 minutes. And we have an expected heating at 0.5 degrees per minute. That's kind of the parameters that are controlling how the converter will perform. On the 230 page, you have more the parameters which are controlling the temperature levels. Where do you want to heat to? We have set now we want to heat up to 40 degrees at the first step, and we have 80 degrees in fine vacuum and parameters like that. We have the vacuum level in the tank during heating set to 40 millibar, so the system will regulate at 40 millibar and heat at that level. We'll look into those more in detail when we're coming step by step. Now we have checked the parameters. We are happy, we are satisfied. We have confirmed the entries, and we are ready to start heating. Now we have to make sure that the transformer is free from people. Have to make sure that the output disconnector is closed, and that we have power. Here is where we are regulating 40 millibar.
25 to 40. Yeah.
25 to 40. I mean, it's going.
Higher than 40 or no?
You can go high. It will regulate around 40. It will.
You could set it for higher.
Yeah, you can set it. You can set it 500 millibar if you want to.
But the best is 40?
It's
Close to the minimum.
close to the minimum. Yeah.
It's still maintaining a good
If you're running an oil spray, then this is good. If you're running oil circulation, this will not work. Do we have the main disconnector closed? Then we're ready to go. We're coming to this page with the green and red stop and start page. This is where we have our phases. We are in off, that's highlighted green. Measuring is now with black text means we can select it. Heating is in gray, we cannot select it. We are in semi-automatic, which is the most normal one that we're going to use. Fully automatic means he's switching between each phase automatically. You will almost never use it. Warm restart, I have not mentioned it before, but if you have done a measurement, you have the initial measurement, you have it matched to your temperature, you can start again using that initial temperature again. So we can click warm restart because yesterday we made our resistance measurement. They are still available on this page, we still have them here. The resistance readings, we have them matched to our 22.2 degrees. This has not changed, it's the same transformer, same connections, everything is the same. So it's not necessary to do the measurement again. You can go to you can click warm restart and we can go to heating directly. We're ready to go for measurement, measuring, click on it. Can go and see what's happening with the converter on this page. We see now that we have closed the main switch, the main incoming power. We have now our 1140 volt on the DC link. And the system is running automatically. And now when the main switch is closed, we also have the lights coming on, flashing on the trailer. So what we can see here is that now he has done the average measurement resistance readings. He has already switched to the lower frequency to 5 millihertz and is ready now to go for high voltage resistance reading. You click on the bottom in the left corner, lower left corner, and you will eventually see what's happening on this one. He's doing it in 6 steps, and we are now in step number 1, which is just a preparation phase. It's a reference reading for the converter internally. Secondly, he's now coming to do the second step. That's when he will take the reading for winding number 1. There is a minimum time and a maximum time up here. The minimum time is dependent on the frequency you have selected. A lower frequency means a longer minimum time. Higher frequency means a shorter minimum time. So if we would have gone to 10 millihertz, we would have a minimum time about 16 seconds. 5 millihertz, 33 milliseconds, and so on.
So if something happens before the 30 or after the 250, there's something wrong? Or?
He will ignore that value, yeah. So you can see that he stopped directly when he was reaching the minimum time. So maybe a little bit too low in frequency, but if it would have really been too low, the system would have said, sorry, it's too low frequency. You can here also see in which phase current is fed and how much. We're feeding 79 amps in phase R.
Let's start on the second winding now.
We're now in phase number 4. Was phase step 4, taking the reading of the second winding.
How come we're only seeing 425 volts? Here.
Yes.
What's that represent?
The output voltage to the transformer. He was having 421 volt output.
I'm missing what that's getting at.
You're confused.
Yeah. Is the maximum output 400 amp on this?
No, the maximum
Or
output
400 volt?
for the maximum output is about 800 volt.
So that's saturated?
That's saturated at this frequency and this voltage, yes.
Okay. So that, okay.
The whole high voltage measurement is to saturate the core to make sure there is no transformer performance anymore. So you're only,
1 hertz.
you would not saturate it.
What do you set at here? Your hertz?
Now we're running at 5 millihertz.
5 mil. So at 5 millihertz, and at 400 and some volts, it draws 79 amps. So it takes 79 amps to saturate that core.
Correct.
Okay.
79 amps to saturate it, 400 volt to push it through.
Yep.
And that is of course going up and down a little bit. Initially you will see some 50 amps before the saturation comes.
Yeah.
When the saturation comes it goes up to 80 amps or 79 amps. Now he has performed the measurement in all 6 steps. We are back in the average mode. We are running at 1 hertz. And now we are performing something that we call demagnetization. Because we have a very uneven balance of the magnetism in the transformer, we are running a sequence of 3-phase heating or 3-phase current to equalize, to balance out the magnetism in the core.
And that happened because it did a resistance measurement on each leg.
Yes, because of the high voltage measurement, because you're saturating one leg.
Yeah.
And if this is not performed, you will have a very unbalanced resistance reading, and the next time you do the resistance
So
reading.
now it's balancing all 3.
It's balancing everything up, it's ramping up the voltage and ramping down the voltage. That's done automatically. Okay, no command, no mode, main contactor is open, grounding switch is closed. We have our, on this omega button, we have our resistance, initial resistance readings. So what we see now here is, first of all, the average temperature for average resistance for each phase in ohm. You have phase R, S, T, X, Y, Z, or whatever you want to call them. Then at the top you have the average of those 3 values. No, that's phase 1, 2, 3, A, B, C. Since we did a high voltage measurement, we have the resistance from the high voltage winding measured, 930 milliohms approximately, and you have the average of those 3. We have now the average and we have the high voltage. The low voltage is then calculated. This is not measured, that's calculated based on the average and the high voltage and the transformer conversion ratio. This is now matched to our initial temperature, 22.2 degrees. Initial measurement is done. We are ready to go into heating. Since we are in semi-automatic, he stopped here. Heating is green, is ready to start. It's black. If we would have had fully automatic, he would go automatically into that. And then when you match your resistance reading from the factory, you're doing it at 20 degrees in the factory. These values will be much higher when you do your 85 degrees resistance measurement.
Right.
So that you can calculate the difference and check the probability of it.
With a conversion table.
Make a conversion. But we are heating to a physical temperature, not relative. To an exact 110 degrees is our normal end temperature. And how that transformer is designed, since we are heating it at the end without any cooling. We don't have any oil or anything cooling the transformer.
Yeah.
So that's not, we are only concerned about the installation temperature. Okay, initial resistance done. We finished the measurement. We're now ready to go to heating. So basically we are standing here now in standby in semi-automatic. Measuring is finished. Heating is the only option we have, so we select heating. We are not logged in at the moment. It logs out automatically after 30 minutes. So once again log in. Pedal login level 3 and go into heating. What we can see here now is that we are regulating the pressure around 40 millibar. As the value was we put in there before. So above 40 millibar he's opening the vacuum valve. Below 35 millibar he will open the aeration valve to get it around there. This vacuum valve is a positioning valve, so he's not fully closing or fully opening. He will adjust it to whatever position is suitable to catch up for the leakage and so on. That's why the alarm is going up, because now it's automatic control, yes.
Don't worry about it.
Now, because we are not running yet, we have charged the DC link,
Trying to equalize the pressure.
and now we're running.
I got it.
What he's doing now initially is taking 6 cycles of 1 hertz to just check that the voltage level is correct, and then he will continue running now for 20 cycles continuously. We have our timer, our 2-minute timer here. We're at 0.4 minutes. After 2 minutes he will check the heating speed. We set that to 0.5 degrees per minute. We will check and see what level we have. After 2 minutes we'll probably adjust the current factor. We are running now at the minimum current factor 0.2. We will go up to maximum 0.5, and anywhere in between he will regulate.
That 20 cycles, is that standard?
That's standard, yeah. And it's 20 cycles, so the time is depending on the frequency you have. If you have 1 hertz, it's 20 seconds. If you have 0.5 hertz, it's 40 seconds. We can see here our set temperature, 35 degrees. Remember, we put 40 degrees as our set temperature, but we have 5 degrees before we're reaching our set temperature. We will do the high voltage temperature reading.
Just to give it a chance to kind of level out.
If we are too high on the low voltage side, we will not be extremely much too high. So we are approaching our 2-minute mark. So we are now at 2 minutes. He will now finish the 20 cycles that follows. Then he will evaluate the heating. We are at 0.2 degrees per minute. We're expecting 0.5 degrees per minute, so we are a little bit below. So he's going to probably push up the current factor from 0.2 to 0.24. It's not a lot. He's careful. He's taking 40% of what he's expecting.
So that'll do it automatically?
That's automatically done.
Up to
Until it achieves
0.5.
Yeah.
Up to 0.5,
It'll
yes.
go up by that increment until it achieves that, right?
Yes.
Yeah, okay.
So now after 2 minutes he will evaluate again. We are at the moment 0.4 degrees per minute. Is probably then, if this stays like this, we don't know yet.
'Cause again, I've seen that fluctuate.
Yes,
Go
it goes
high
up.
and then
Goes up and down a little bit, yes. It was 39, now it's 0.24. That's why we're not reacting immediately on each temperature variation
So you have that 2 minute.
for stabilizing. We have to remember it's a physical unit that we're heating up. Temperature distribution goes. It takes time to equalize. You have your on this resistance page. You have your temperature here,
And what is it right now?
23.5. So again, approaching our 2 minute mark. And once again, he was increasing from 24 to 27.
We're at
He was at 0.3.
So he's going to keep doing it until it achieves the 0.5.
Yes. So after he's at 0.5, he will basically doing the same all the time. After 2 minutes, each 2 minutes, he is evaluating the temperature increase. No, he will not. He will not warn you if he's not achieving this here. He will only warn you if you're not achieving your set temperature within a certain time. Remember from yesterday, I showed you that there are timers on this button with the pages. There is a timer here called set to MX, maximum time until temperature T1 reached in heating. So if you're not reaching your temperature here within 5 hours, then he will give you an alarm. Now you go up to 20, you go up to 90 degrees, and then you will do a stabilization period. So you will do some reheating up to 90 degrees within, you have a heating break of about 2 hours, then you reheat again to 90 degrees, then you have another heating break of 2 hours. So doing that over a period of time, let's say 12 hours or 24 hours, you're stabilizing at your level at 90 degrees. And because here,
So I should be able to rate you. So if I come in and it's at 80 degrees, I want to go to 90.
yep,
I should be able to do that within 2 hours.
that's reasonable, yep.
Stabilize it for a couple hours, reheat for 2 hours to 90
No,
degrees.
no, you heat up to your 90 degrees.
Yeah.
When you're reaching 90 degrees, then you wait 2 hours, and then you reheat again, because then you drop the temperature down to maybe 85 degrees, waiting another 2 hours, and reheating again after 2 hours has elapsed. That's automatically done. You set a parameter for that. Not really. That is at those levels, at 90 and 100 degrees, you're going for experience based on the size of the transformer. Bigger transformers, then you need to do more cycles. Smaller transformers, then you do fewer cycles. So let's say a 100 MVA transformer, maybe you can dry out in 4 days. A 750 MVA you have to dry out in 7, 8, 9 days. So, and this time span difference is taken in 90 degrees and 100 degrees. But also the VZ406, the water extraction measurement device, that one gives you a value, how much the water is coming out. And even though you get a plan, I would suggest that you have a reference number. Check this, that the water extraction is not higher than 50. Because if it's higher than 50, then it's extracting more water than you expected. And then you should probably do one more reheating at your level before you go to the next one. And that is exactly what you have to. That's why you cannot go into fully automatic. You have to take that decision at some point. Yeah. So the converter stopped for some reason. We get an alarm. It's flashing up on the alarm bell. We click on it and see. We are getting the similar voltage as same as yesterday, but this time it's high voltage on the DC link.
But that was the alarm we got
The last one.
alarm
Yes.
we got. Then another
The-
voltage reading.
This I have a voltage sensor measuring, and that is protect the capacitors. It is on the DC side, yes. The DC link is, like you said, seen 1140 volt normally. At 1200 volt it cuts off, and it's the under voltage is tripping at 800 volt. Let me do a little bit of calculation and see what I'm expecting to get in for this voltage to appear. Because if the voltage is going from 600, I don't know how high it goes. Of course, that's directly affecting the DC link. When you have an alarm like this, you have to reset it. On the same page as start and stop, you will have a button called reset LFH error. That's highlighted red. Before you press that one, you should check the DC link voltage. This one here should be below 42 volt. If you're not, it will not be able to reset, or it will reset, but you will get the alarm back to it. So you can reset by clicking. The alarm here is
Voltage was higher still than 40
it would not allow you to reset it if you have more than 42 volt. The alarms are cleared. You can click them and get the acknowledgement in the right. The converter will start now automatically again. I can run the logger like we did yesterday. We got the same error again, yes. Now we got the logger.
I ate it all on Gary.
Here we're 1260, 1260, 1270.
So is this the period where it's charging up?
No, here's running normally. This is in normal operation. This time frame is 7 seconds.
Okay.
And I mean here is a current going out.
Which one?
The output current, the three phases
Okay.
here. And here is a DC link voltage. And at that time something happens. No, it's 1200 for over voltage. 1200 volt on the DC link.
Your normal is
1140.
1140. So you've got
60 volt.
And you have 60 volts on the other side as well? For the under
800 volt. 800 volt is under. Yeah. I mean that's not dangerous for the equipment.
But why?
But there he was tripping because he got an undervolt. The voltage was too low. So one contactor was opening, which opened the main contactor. That I'm quite sure about. We have now finished the initial measurement. You can see that on the start and stop page that the measuring phase is done. We are green. The text for the heating is highlighted black. We are in semi-automatic, so we cannot. The machine will not go on to the next phase without we taking the measure to click on the heating button. So we check our values. We have now the resistance measurement on the high voltage. We have it for the low voltage. We have also the measured average resistance. This is now set to our initial temperature, and that's what's so important to check, that this is 50 degrees is what we put on the hand page as 50 degrees down here. Since we are preheating the transformer, the resistance values are higher than before, but they are okay. Low deviation between the phases, and we are ready to go on. So go back to the start and stop page. From the start and stop page, we click the heating button. The converter will wait a little bit, and then he will go on, start heating.
The frequency is still 0.7, is it?
We still have a heating frequency of 0.7 hertz. For average heating, we have it 0.005 hertz, 5 millihertz for high voltage heating. In the parameter page, we have set now the average temperature for the heating to 65 degrees. We have on the common page the parameter temperature difference for starting high voltage, low voltage measuring is set to 5 degrees. 65 minus 5 makes 60 degrees. We are now heating up to 60 degrees centigrade. Then we take the measurement to check the temperature difference on the high voltage and low voltage. What's interesting on this page is to monitor the current factor. The actual current factor is 20% of nominal current. The parameter is 20%, so that's reaching that one. We have the timer, the 2-minute timer. After 2 minutes and 20 cycles, he will adjust the current factor if necessary, based on the temperature increase. We have now set the temperature increase to 0.90. That is a little bit high for what we want, so we reduce that one on the parameter page. under windings. There is a parameter here. Temperature rise per minute during heating up, temperature rise per minute during stabilization. We keep that one at 0.5. Then we can go back to our converter overview page. We have this now changed to 0.5 degrees per minute. Initially the converter is ramping up the voltage to not overheat it. So you see now we are at 0.2 current factor. The heating up is quite low, 0.1 degree per minute. After 2 minutes has elapsed and 20 cycles, he will adjust it. Output current, 63.9 amps. We have another output current indication up here, 95.7. That's a maximum peak current. The actual power is calculated based on the frequency, the voltage and the current. So this is actually the power output. It's not the imaginary power. It is it's the real power, yes. The reactive power is not in here. So if you increase the frequency, the voltage will go up, but the power will remain the same. Like I mentioned, heating current 64 amps. Our measured temperature, the average temperature is 50.1 degrees. We have our output voltage and we have our estimated output voltage. These are normally not matching so well for several reasons, because we are controlling the output current and then we are just calculating what we expect as a voltage. This voltage is not a reference for the converter. We can see from the top rows, first of all, the error number. 0 means no error. And we also have the intermediate voltage. That's the first DC link. That's pure rectified from the net grid voltage. We have the second, that's the output DC link shown. We have the percentage of the chopper working, that's output chopper, regulating the, taking care of whatever energy is coming back from the transformer. So if this voltage goes too high on the output DC link, the chopper will burn it in the chopper resistors. And these two last values are the peak values of the voltage and the current. On the resistor page, we still have our initial resistances. At the bottom part we have the actual resistances. Since we are only running in average mode, which is 0.7 Hertz in this case, we are only updating the average resistance. The high voltage and the low voltage resistances will be updated later when we stop heating, take the high voltage, low voltage measurement. That's when the new values are coming. So that reading is coming 5 degrees before our set point in temperature. The set point is 65 degrees, 5 degrees before is 60 degrees. In the lower left corner we have the deviation. If you have some kind of problem, some kind of issue with the transformer, you will see deviation in current, voltage and resistance in this. And that's measured in percent. That's a deviation between the windings. If you're feeding it unevenly, if they have an issue with the tap changer on one phase or whatever it can be, you will have here. You also have an alarm level. Now this one is set very very high. Alarm level normally is 10, 15% deviation. So when you get this deviation, you should check cables, you should check everything externally here, all connections. You should also check the short circuit bars, that you don't have an issue there that could affect it. Lastly, I mean, there can be an issue inside the transformer, that something has fallen loose or you have a short circuit, maybe by the PT100 if you have damaged the insulation or whatever.
So I'll go over it again. The first one is what again?
The first one is the voltage, the difference in voltage between the phases.
Okay.
The second one is the difference in current between the phases that we are feeding.
Yeah.
The third one is the difference in the resistance between the phases. Yep, we take them down directly.
You can manually change that.
Yeah, we can manually change it. That is
Common parameter.
common, on the common page on the parameters, maximum current deviation. And this is when you will have an alarm and the, now I'm logged out. You put it to 10, 10, 15. Going back to our resistance page. So, when the deviation in voltage goes over 10%, the converter will stop and you will have an alarm. Asymmetric voltage, asymmetric current, asymmetric resistance. First of all, check that these values are not set to 1 or something then. That they are really up to 10, 10, 15. Then, secondly, check your connections. Internally in the converter, internally in the trailer, on the cables, the bus bar, the tap. I doubt it, but I mean even the disconnecting switches can make an issue. For yeah, if you have more than this, then you have an issue with the transformer.
So we won't have it any higher than 10, 10, or 15.
No,
Wouldn't set it any higher.
you wouldn't set it any higher.
We wouldn't set it any lower either, or that's where it should stay.
That's a good level.
Yeah.
Yeah, generally all
It should stay set.
all parameters under common you normally do not have to touch. They stay like that. That's why they're called common. Fix you cannot touch. They are fixed.
Unless somebody wants to mess with it.
And the 230 is more process related parameters. How long waiting times, when do you start heating up again, to the temperature levels and so on.
New mouse.
And the winding parameters are for regulating the converter. That is, these parameters on the winding page relates very much to the behavior of the converter on this page. You have the current factor, you have the heating up time, temperature rise per minute. You have the period for checking the temperature rise. You have the frequencies for average and high voltage. This factor UOH, I explained it briefly this morning. The converter normally remembers what voltage it was working at the last time. Let's say it's working at 500 volt output voltage at average. When we're switching over frequency to high voltage measurement, we're reducing the frequency considerably, and we do not want to overfeed the transformer with current. So this factor gives you the ratio of what he should do with the voltage when he's switching from average to high voltage. This factor tells you that he should use only 50% of the old voltage. So instead of 500, he will start with 250 volts when he goes into high voltage heating. And that's because the resistance of the transformer changes dramatically.
As it gets hotter.
No, not when it gets harder, when you're changing the frequency. Because when you're changing the frequency, you kind of disconnect the low voltage side. And if you look at this frequency page, resistance page, average resistance when we're running at 1 hertz, 0.7 hertz, the resistance we see is 2 point something ohm, 2.2 ohm. The resistance of the high voltage winding is 1 ohm.
Right.
So if we are feeding now only the high voltage side with the same voltage as we had when we had 2 ohms, we are doubling the current. And then we risk that there is a risk that we go into overcurrent alarms initially. So this is an aid for the converter to get a correct voltage, initial voltage for the high voltage measurement. After that, he's of course regulating again, but that's just for indication. If it is a major difference between the high voltage and the average resistance. We can see here it's approximately a factor of 2. High voltage resistance times 2 gives the average resistance.
That's a rule of thumb. Like,
Rule of thumb is 40-50%. If you have a transformer that is giving you an extremely low resistance reading on the high voltage side, then you have to take down this factor UOH. U stands for voltage, and OH is a German Oberspannung.
What?
So you can see high voltage in German. It's a language lesson as well. So it really explains here in the parameter what it is. You have the high voltage is equal to the average voltage times this parameter. So if the average voltage is 500 volt, you take this parameter at 50%, you get 250 volt out. So with that explanation text, you can refresh the memory. We have this parameter T jump factor applied for alarm if temperature changes too fast. Degrees per minute. So that's what I'll say, that if the temperature changes 10 degrees per minute, then you will have an alarm.
That's huge.
Oh, it's a huge step. I mean, that's then something has happened. I mean, that's when the bus bar is melting on the secondary side. Because it is impossible for the temperature to change so fast.
Quickly, yeah,
No.
it's impossible.
You have 100 tons of steel, cannot change that fast. So this winding page is very much the behavior of the converter. What will the converter do? The 230 page is the behavior of the process. How do you want to dry out the transformer? Temperature settings, waiting time, stabilization times, vacuum levels, and so on. The common ones, set them once. You should be aware that if you need to change them, they are there, but generally you do not have to change them. Then we're coming into the VZ406. That is a measuring device. We'll take those value readings. This is showing the pump curve, the pump characteristic, the suction capacity of the vacuum pumps. And that's what we are measuring with the VZ475. Everything this is shown on this screen here. The pressure curve is only giving you the correct value for the VZ406 readings. If you have an incorrect pressure curve, the readings will be incorrect. And this one will give you the value in extracted water in grams per ton insulation per hour.
Sure.
And if you have incorrect, you will have a higher or lower value depending on how your curve is. So this is where the insulation weight comes in. This is where your suction capacity curve comes in from the vacuum pumps. And this is the device that we hooked up over the roots pump. Now we have turned off the roots pump. We have connected the VZ475. We'll take the readings for that pressure curve to see if we can match it to the actual one. You don't have to compare it. This will be, we have the calibrated values. We know the values for the leakage value. What this one does is we have a calibrated leakage. We are assuming that the system is vacuum tight, and then we open a valve here, and then we know that how much leakage this one is generating. The pressure sensor inside this VZ406 is then taking the end value. How deep do you go in pressure? And in that way you can take 10 measuring points and monitor the pressure curve. So we are coming closer to our set point. 60 degrees. We have been heating by 0.48 degrees per minute, 0.5. Okay, we are very close. We can look at the trend curve. The trend curve looks empty, but you have to set the initial time when you started the process. You do it by clicking here on the time. Start time, click on the numbers and increase them. It was about 1 o'clock when we started. Maybe a little bit less. We take 1250. Okay, click on the date, set OK, and exit. Here now you can see these 8 values. That's the average high voltage and low voltage temperature. You have the fine vacuum, you have the coarse vacuum, you have the water extraction for the process, you have how much power you have used, and then you have the temperature rise per minute. These are color coded. You have the minimum value, you have the maximum value for the scaling. These are the same values as you see here on the side. So if you want to change the scaling, for example, average temperature, you don't want to start at 0, you want to start scaling from 40 degrees. Just click on the minimum, change it. The scaling here changes, and you see a little bit different resolution on the screen. Very convenient is to have the same scaling for all temperatures. Otherwise you will get a little bit confused. You can click anywhere in the screen. If you just click here, you will have a line coming up, and here you will have then the exact data for that time period, for that time. The date and time, and you have the trend values for that one. You can also zoom in this screen by clicking, holding, and dragging right. Then he's zooming in here. And you can zoom quite a lot. Then you see here your time range, 1313 to 1314.90. So that's 1 minute 20 seconds time frame. And then you can follow the curves jumping. You go back to the original zoom by clicking on the this graph button. You're coming back. Here you can have some fixed zooms, 3 hours, 6 hours, 1 day, 5 days, up to 10 days. Going back to your 3-hour zoom. These 8 values, you can select any 8 values you want from the temperature page. Everything that is highlighted green you can select. You just take the number corresponding to this one. Object temperature 1 is 1, and so on. If you feel that you want to have anything else logged, you can click on one of those and it saves those values as well. Converter has stopped. Average temperature at 60 degrees. That's the time when you want to do the high voltage measurement. So he will now switch he will now make another average measurement reading for the temperature. Then he will go into high voltage measurement to see the temperature difference between the windings. So first, our normal frequency, 0.7 Hertz. He will run 6 cycles on this to take a temperature reference reading. Four, 5, and 6. Now he will change the frequency to our high voltage frequency, which was 5 millihertz. So what we see here is we are now at 59.9 degrees average temperature. The interesting question will now be how warm is the high voltage windings and how warm are the low voltage windings. Coming from here, going to the high voltage page, you also have the same button up here. This is a 6-step procedure. First, he's magnetizing one leg, then he takes the readings in the second phase. He's taking them phase by phase. You have the minimum time, 33.3 seconds. That's based on the frequency you have entered. Lower frequency means longer time, higher frequency shorter time. You have a maximum time. If he's not reaching saturation within this time, he will stop and telling you that the frequency is either too low or too high. So step number 2 is finished. We're going into step number 3. We have taken our reading for the high voltage side on phase 1, 1 point something ohm.
What was it before? Is that still up there? Base one?
It was similar before.
Very close.
I mean, initially we had 1.01.
Yeah.
Now we have 1.03. So it has increased 3%. Each percent is approximately 3 degrees. We have been heating up 10 degrees. It should not be so much difference between the high voltage and low voltage. Phase number 2 is finished. Running in preparation phase number 5, switching to number 6. Phase number 6 is finished. We are coming back to our normal frequency, and we do now what's called a demagnetization. You are stepping up the voltage in cycles of three cycles at each voltage level, and up to the highest voltage level where we will run 20 cycles. And this is to even out the magnetism in the transformer. During the high voltage measurement, you're feeding a lot of magnetism into one leg, which means that if you directly start taking the measurement, you will have a very uneven balance between the windings. So we are taking now 20 cycles at our highest voltage that we're operating at, 0.7 hertz, and then we'll slowly step down as well in sets of 3 cycles. Preset, you cannot change them. You will not find the values for it. It's not visible on the visualization. It's everything deep down in the program. The program is 2 parts, or several parts, but one is focused on the converter and one is focused on the process control. And we have been working more on process control, and we have 2 other companies be working on the converter control. The competitors are trying to, but they are not so successful. They have had big problem to get the resistance reading under control. To get a uniform heating is a big challenge to get this straight line. I know it took half a year before the customer even accepted the factory acceptance test. And then when they came to site, they were able to drive 3 defined transformers, nothing else. I mean, what we have been working hard on is to get the resistance reading so accurate that we do not need a temperature sensor for following the temperature in the winding.
Oh yeah.
For this application, it is not that crucial. It is important for an accurate and fast heating, yes, because we see here that placing of the temperature sensor is very important for its readings. In distribution transformers, you do not even want to open the lid or the cover anymore after process.
Right.
You just disconnect your 3-wire power cables, you take away the short circuit bar, and off you go to the test bay. Because the transformer is already oil filled. So you don't open the cover anymore. We don't use oil spray in those anymore. We're using a little bit hot air support, and we're feeding hot air through the oil filling valve. So we were taking our temperature readings. We were at 60 degrees average, high voltage 55 degrees, low voltage 72 degrees. So even at this small temperature step, the temperature difference came quite high. Yeah, we are measuring the high voltage, we are measuring the average resistance. Resistance temperature, that's the same.
but is it? Okay, alright.
We are calculating the temperature based on the resistance. So what we do now is that we continue heating up average up to 65 degrees. So from 60 degrees up to 65, and that's where we will do the stabilization. Here we have the average temperature, here we have the high voltage and low voltage temperature. If we zoom in here, he's adjusting now these two levels to whatever we got, the result we got. So they remain constant here because we do not measure it. We don't know what's happening with them. And then you have a step temperature here. That's, as we discussed before, cannot happen, but we cannot measure the separate windings temperatures in any other way. So we have selected to keep the constant temperature and make the step. When we're coming into the heating break, we can make the suction capacity measurement on the vacuum pumps. No, we are in the average.
Pardon?
We're in average mode. Here you can see that it's,
That says AV mode?
here it says AV mode, average mode.
Sorry, not wearing my glasses.
What does that mean?
It means that we are heating in average mode, both windings
You wanna bring up
simultaneously.
a-
Distribution transformers we heat up from dry insulation, not oil soaked, up to 120 degrees. You can set that to 5 degrees per minute or something. I mean, something distinguishing. But you have to remember this 10 degrees per minute is not a temperature increase. It is a resistance change indicated by a temperature increase. But this resistance change has happened because of some reason. We can set it to 5 degrees. I mean, that's fair enough. If you put it too low, 2 degrees per minute, then it could actually be the measured temperature increase that we do. What you want to catch is if the soldering is bad, if a bad connection, bus bar is melting or whatever. And if I put 1 degree per minute and you put the alarm level at 1.5 degrees per minute, you never know if it's a bus bar or whatever it is.
Right. Okay.
Five, I'm fine with 5, but I'm not fine with 2.
Two's too much.
2 is too low, yes. If I make a slight mistake in the reading of the resistance in the converter, then you have an alarm which you do not know if it's coming from the converter, from the measurement, or... So, we reached 65 degrees, as expected. Everyone's happy. We have now 2 new timers running. This is timer Z3X and Z4X. These are our stabilization waiting timers. They are in this example set to 4 hours and half an hour. This means that we are waiting now half an hour, doing nothing, waiting the temperature for the temperature in the transformer to stabilize. Radiation between the high voltage, low voltage, and to the core. So after half an hour, we'll take a new reading, take a new measurement, take a new temperature reading, and heat up again to our 65 degrees where we are. When we're reaching 65 degrees, wait another half an hour. Stabilization, yes. On this page here,
So what's
you have the process.
4-hour time period there then?
The 4 hour time period is how long we keep this stabilization.
Oh,
Heating,
okay.
waiting half an hour, heating, waiting half an hour for 4 hours.
Okay.
And that's now just in factory testing that we do this short heating breaks. Normally you take, when you're heating up from 80 to 90 degrees, then you go for 6 hours or 8 hours heating breaks. So looking at this picture here, which is describing the process, we have been heating up from our initial temperature value to our set point. In between here, you have your 5 degrees when you're taking your high voltage readings, and then we're heating up here. So now we are at point T1, stopping, and the temperature will drop. After half an hour, we'll take a new reading and heat up again. Stop for half an hour and heat up again. And after 4 hours, we are at this point. He will go into evacuation phase, waiting for the pressure to go down, and heat up to our next level, That one is in fine vacuum 1 phase. That's our next temperature set point. So first waiting 4 hours for stabilization, evacuation, heating up in fine vacuum phase.
There?
Here, between here and here, you see here it says oil drainage. Yeah, I mean, normally you're running oil spray circulation.
Sorry?
You're running normally oil spray. Then it looks more like this one, this picture. You have two process pictures. One with oil spray and one without oil spray.
Okay. Alright.
You're heating up,
Yeah.
doing your stabilization.
Yeah.
Evacuation is only heating up. There's no oil drainage in this one.
Right.
In the other one, you have an oil drainage phase where you're draining the oil from the transformer tank. So you're heating up to your fine vacuum value and doing the next stabilization phase. If you're not reaching your temperature that you want to reach, then there could be many reasons. And all reasons are here. You have your actual power. You can limit your output power to whatever source you have. If you only have 50 kilowatts, maybe 50 kilowatt is not enough for heating up.
Right.
It can be that your current factor is set too low, the maximum current factor.
Right.
If you set it only to 25%, maybe you're not reaching the temperature increase.
Well, you should catch that before you run out of your...
Well, if you do not catch it, you will have an alarm. You see that on the timer page as well. Maximum time,
2 hours, isn't it?
4 hours it's set to. Maximum time until temperature T11 is reached in evacuation fine vacuum. So if it takes more than 4 hours to go from the set point we have now, 65 degrees, up to the fine vacuum set point, if it takes more than 4 hours, you will have an alarm. The system is unfortunately working on a base of 10. So even time is working on a base of 10, which means 0.5 hours is half an hour, it's not 50 minutes. 0.7 hours is 45 minutes, 40 minutes. Can be confusing when you're setting the timers, but it's important to remember that that's how it's working. So we are now at 0.10, which means 6 minutes. What we normally do now, we said we want to do the suction capacity measurement. 475, yes. We want to know that we are back here before the converter starts again. So we set this braking time long enough for us to be able to come back. It is now half an hour. We don't know how long it takes. So put this value now to 4 hours. When you come back, you reduce it again, so it starts when you're back.
Which one's that?
This is now the timer called Z4X. Duration of heating break in heating.
You want to make that longer now.
There are two things, temperature stabilization time and heating break.
Yeah.
So the heating break we have under
Something to fix it.
the process page. Here's the duration of heating break, row 14. Row 14. Logging in, take a value, 10 hours. That should be enough. Then the plant will not start until we are back. What you should do now before you do this vacuum capacity measurement, make sure the vacuum valve up here is closed on the transformer. Click on it, put it into manual, and it will close. And will keep closed. You see the text goes to blue instead of black, and it will be closed. We turned off the roots pump before. We have connected correctly over there, so we can start the capacity measurement already directly from here.
So to toggle that again, Martin, you just
You
click
click on the valve, go into manual, and that's it. Because then we shut off the transformer. The vacuum pumps are pumping on a only to close valve. The valve will not open from here. So go to the page, the green box. The former generation of this VZ406 was green. Now it will change the color to red. So, okay, we will now do the suction capacity measurement for the vacuum pumps. We make sure that our main vacuum valve is closed. Coming from automatic, put it in manual and keep it closed like that. In that way we will make sure that it's not opening, it's not halfway open, it will go to fully closed. The screw line pump, the vacuum pump is running. We are connected then on the our devices, the VZ475 and the VZ406.
But that's not our pump, is it?
No, I'm not controlling your pump here.
Yeah,
This is just a visualization.
your standalone.
Yeah. So you have to make sure that your screw line pump is running.
Yeah.
Normally the booster is running as well, but now we have a special connection on this setup. The VZ475 is connected between the booster and the vacuum pump. And the VZ406 is connected over the roots pump. In your case now you only have one connection point. If you connect them directly on the same T, you will have a bad reading here because the air inlet here will go directly to here. So what we have done is that we have turned off the roots pump, we have taken this line, connected it on this side and the leakage air valves here. This 475 is a set of 5 calibrated valves. It will make a certain leakage rate for each valve that is open, and it's making 10 combinations of these 5 valves, taking the readings and from there calculating the suction capacity of the curve of the pumps. To make this reading, to make this measuring is quite simple. You click on this gray button once, it starts, and he will start making the measurement, taking the measurement. We are using the pressure sensor inside the VZ406 for this case. That's why it's important that this side, the high pressure side of the VZ, is connected to the line, as well as the VZ475 is connected to the line.
This line.
Yeah, the VZ406 is not unique. It has
a
plus and minus. It has a transformer side and it has a vacuum side. So the whole theory behind this is to measure the end vacuum for each leakage level. What is the best vacuum we can reach for each predefined leakage? Inside the VZ406 there are 2 valves. There is one valve on each side of the measuring chamber, and we're only using one of the valves to expose the pressure sensor. So in the first stage we're using one valve, second stage we're using another valve, third stage he will use a combination, and so on and so on. This whole VZ is telling you how much water you're extracting in the end, and it has to match that because it's working on pressure differences, and the pressure difference is depending on how strong your vacuum pump you have.
One out.
Yeah, but we are not measuring the moisture at the moment. We're only measuring the suction capacity.
Yeah, good.
Yes, it will. But now the valve to the transformer here is closed.
Yeah.
So there is
No, I thought you were just talking about for when it's doing the reading.
Yeah, when the 406 is doing its reading, it will be the end pressure will be affected by the vacuum pump capacity, which we are measuring now,
Yeah.
and it will be affected by how much water content it is in the vacuum coming out. And that's the whole idea. We are making those 2 differences. I would take a reading for each degasifier, yes.
Pump is not going to suck the same.
With the screw line pump you are quite good because they are quite constant, but especially when you have an oil lubricated pump, a rotary vane pump, then you for sure will change with the age and the quality of the oil.
But each screw pump,
And the piping layout in the degasifier will make a difference as well for suction capacity. So for every setup, every new degasifier, make a new reading. It takes you 10 minutes and then the reading is done. This information we achieve is automatically saved in the parameter list. So you do one click, you wait 10 minutes, measurement is finished, and the values are saved.
Okay.
401. On this page, the parameter
Yeah.
and the VZ406.
Yeah.
you have the suction capacity here. You see everything is 0 at the moment.
Yeah.
Here it will be filled out the values from this reading.
Yeah.
And then you have the suction pressure for the vacuum pump and the corresponding pumping speed. You can save this and reference back to that. Yes.
So you would label that as
You can save it here. Call this factory setup.
Yeah. Where do you get that from? It was down there.
There was a little floppy disk.
On this screen where you have the VZ406 and VZ475, you cannot save it.
Okay.
Here is just where you're starting the process, the reading.
And where did you go to save it? And where did you
It's on the parameter page,
Okay.
and then you have the 5 different sets of parameters, the 406. Change back to the other converter and run the same heating sequence on that one.
Speed dial.
Okay, so the suction sequence is finished. We have gone through the 10 sequences. The final one is with the closed valves, all of them, and taking the final pressure. We go to our parameter page,
So now you can save that.
and now you can see that we have increasing values. And that's the key. The values have to be increasing. And we should change the last value here. It's 300 cubic meter per hour. That should be your nominal suction capacity, which is 1260 cubic meter per hour.
Why did we change that?
Because that should be your nominal capacity of the vacuum pumps.
You should
Oh, I
change
see,
that.
okay.
You should change the label on that line.
To nominal.
Yeah.
1260, 800, 500, 300,
And
220, 150, 100,
they
100,
should get
48.
higher. Why?
We are measuring the pumping curve, and that is an increasing curve. So we are stepping step by step to more and more leakage rates.
Okay.
So if they are not continuously raising, then you have something error in the measuring. That's the only check you should really do here, to see that that one value is higher than the previous one. What you're missing is that when we are running the 406,
Yeah.
we are running at different vacuum levels.
Okay.
And depending on which vacuum level we are running, the vacuum pump has different suction capacity.
Okay.
This suction capacity affects our reading in the chamber.
So it did 5 different readings to give it different ranges.
He's interpolating the pump curve. We have 10 points we have. So based on our vacuum reading here, we are taking from our readings in this curve. If you draw a point-to-point line here, you'll have a nice curve. And based on those readings, you will then deduct the suction capacity from the pressure reading in the VZ406. It's an automatic calculation in the program. If you do not have this VZ475, it's broken for some reason, you can also enter these values manually here. If you have the pump curve from the manufacturer, you can just enter these 10 points. And then you click on this icon up here to save it.
Okay.
You load it,
So
high bay. So you have your high bay.
Those are my levels though.
We can change a value. Change this 1260 to 100. Go to your open file. Click on the high bay. Click on OK. And you get your values back here. Fair enough. We maybe should do our heating. We go back to automatic on the valves.
you have to do a measurement, don't you?
We have our timer, which has now not passed 10 hours, but it has passed 0.89 hours.
Yeah.
So if you now change our parameter back to, instead of our 10 hours we had here,
Yeah.
duration of heating break, take to 0.9 hours.
Oh, because it was at what, 0.89 there?
0.89, we are 0.9, so timer has basically elapsed. He will now do the next measurement in the stabilization phase. The next heating up.
Oh, you gotta put in the timer. Did you miss the timer maybe?
No, he has to pass. He has to pass the timer.
Oh, okay.
We are now in measurement.
It's in measurement now.
It is selected here now that we should do high voltage heating in stabilization. High voltage measurement in stabilization. So he's doing this now actually. So what he has done is that he's going into AV and HV mode, average and high voltage mode in measuring. And we are now in second phase, so he's taking the readings, which tells us that he's taking the temperature readings. Temperature reading at the high voltage, 57.5 degrees. I think we are in demagnetization at the moment.
What was the low there?
72.
He has not calculated that yet.
Oh, okay. There was a value.
It's an old value. It's updated after demagnetization. So we are still at 73 degrees on the low voltage, 61 on the average. And since we are so high now at the low voltage, he will not do anything more at the moment. He will wait approximately 10 minutes, and then he will do another high voltage measurement, high voltage reading, for waiting for cooling down. To start with, you have selected here to do the high voltage thing in stabilization phase.
Yeah.
If you deselect this now, you can do that. Then he will not do that. Then he will go for the average heating and behave more normal. This is something that you can select to do, the high voltage measurement. Can be good to have it if you have a big temperature deviation between the high voltage and low voltage.
Yeah.
But it's also a little bit unnecessary since you have already taken care of it 5 degrees before. So most of the time it is good enough to do the high voltage measuring at the initial resistance, and then you can do the high voltage measurement here 5 degrees before your set point, and you're fine with that.
That's enough.
It's enough. No, it's not changed. It's only 5 degrees on the average. And they're following each other fairly good, and now we have been stabilizing for 1 hour. So that's also the reason why when this was designed from the beginning, they want to give full flexibility, full security. All cases of transformers showing up. It ends up to be a little bit too many options, too many features that you can do. And in the end, it's a big question why to do it. So since we now deselected that one, he's now heating average up to 65 degrees.
The low voltage winding?
No. We're at 75 degrees at the low voltage.
Okay. So, because you have the other set point that you can look at, when it gets within 5 degrees, it'll stop.
No, we are at 73 degrees here at the low voltage. I'm not concerned to go higher, go up to 85, 90 degrees. That's fine. So now we have changed and running at 1 hertz to test that the system is running for 1 hertz as well. We are now at 63 kilowatt output power. Heating speed is half a degree per minute. Put it up to 10 hours. Day is over. My name is Martin Karlsson, working for ABB Micafeel in Switzerland. We are the supplier of this unit called low frequency heating unit. The low frequency heating unit is designed for drying power transformers out in the field or as a repair facility in the workshop. The principle for using the LFH is to use the natural resistance in the transformer. That is to heat up the windings from the copper resistance in the winding by feeding the high voltage side with current. The low voltage side will be short-circuited, and in that way the nominal current will be fed both in the high voltage and the low voltage side. The benefit of using a low frequency heating is that you're reducing the frequency from your nominal 60 Hz down to approximately 1 Hz. By doing this, you can also reduce the voltage needed to induce a current. The transformer will still have its transforming effect, which induces the current on the low voltage side. And by having this, you can supply then the nominal current on both the high voltage and low voltage side with a minimum energy required. The main benefit for using the low frequency heating compared to other conventional method is that you're heating from inside the transformer core where the copper resistance is and heating outwards. This is the same pattern that the water should go for evaporating and drying the insulation. The low frequency plant consists out of one major unit, and that is a frequency converter standing behind me. And then there is a control system controlling the frequency converter. It's also controlling the other equipment connected to the plant, such as the vacuum valve, the pressure sensors, the thermocouplers, and the vacuum pumps. We will now show you a demonstration about the plant, how it is working, how it is set up, the main components, and equipment around the plant, how to connect them to the plant, and how to operate the plant. What we see here is a frequency converter. It takes at 60 Hz from the input, converting it to 1 Hz output frequency. In between we have the DC link, we have a secondary DC link, and we have some contactors and fuses to protect both the equipment and the transformer. The incoming power is down here. The 3 cables, 600 volt, 60 Hz coming in. They go through this main contactor, which is a main contactor supplying power to the DC link. The cable from the main contactor goes over the blue transformer, input on the right side, output on the left side. This blue transformer is then coming up over 2 rectifiers. This rectifier is the one generating the DC link. There are 2 rectifiers in parallel, one on this side here, and the second one on the back side of this cooling flange. The capacitors for the DC link are found in the back of the converter. This is the incoming 600 volt 60 Hz power supply. They go through this main contactor up over the blue transformer. This is the inside of the transformer. This is the outgoing side from the transformer. From here they go up to the rectifier, which is rectifying the incoming voltage to the incoming DC link. The rectifier. Capacitor for the DC link are to be found behind and under these resistors. The input DC link of 1100 volt is transformed over this red reactance to the secondary output DC link, which is then matching the output voltage. The output voltage is then in 3 stages, 1 for each phase, controlled by current and voltage to supply the transformer its correct values of current, voltage and power. The capacitor bank is consisting of 3 capacitors in series, which can be found in the back part of the converter. They're all called the RIFA and has a capacity of total approximately 1320 volt. On the output DC link there is a IGBT in the black box with its control board. This control board and the IGBT together forms a chopper. If the voltage at the output stage is too high, the chopper can burn the excessive energy in the chopper resistors. There are 2 sets of chopper resistors, one at the top and one at the bottom. Each set consists of 6 resistors where the energy is burned. Each resistor takes about approximately 100 watt. The entire converter has 6 IGBTs. Each IGBT is built up by a control board and the IGBT itself. Firing the IGBT is controlled over an optical link. The optical link has 2 firing signals at the outer and a return signal for error at the middle. There is a second signal for the control board, and that is in this flat cable, and that's mainly controlling the temperature of the IGBT. To prevent the converter from running when the doors are open, there are 2 switches, one for each door, which will stop the converter whenever the doors are opened. Between the converter and the transformer that we're going to dry, there is a safety switch. This disconnected switch has to be closed when the plant is supposed to run. And when you're leaving the plant, please open the switch to ensure that no current is injected to the transformer. This part here is a master control for the entire LFH plant. It controls the converter, and it also controls all the external devices. It communicates with all the input-output boards through an optical link, and it communicates with the laptop over an Ethernet cable. The input-output cards are connected over the optical link and are placed throughout the converter and throughout the control cabinet. This is a digital input-output card. It has 16 inputs and 16 digital outputs. There are separate cards for the analog input and outputs, and also for the temperature sensor inputs and outputs. In order to prevent damage to the converter in case of power failure, there is a UPS installed in the control cabinet. This UPS has to be turned on prior to operation, and is turned on by pressing this button, and the startup is automatic. Here is a main incoming power supply for the converter. It has 600 volt in 3 phases, 1, 2, 3, and it has a ground connection at the bottom. They should be matched to the power supply wherever you're coming from, and it should be ensured that you don't mix these power cables with the power cable on the other side of the trailer, which goes to the transformer. The 3 main incoming power cables, 1, 2 and 3, plus the ground power cable. This is the other side of the trailer. Here we see the power supply going from the converter to the transformer. We have 2 connections for each phase, and we have 3 phases. Additional to this, we have the grounding cable, which should connect the transformer tank to the converter via ground. Normally, for major part of all operations, you use 1 set of cables, which gives 1 cable for each phase. The second set of cables is for when you have transformers which require more than 350 ampere of supply. Then you connect the second set in parallel with the first one and connect it to the same phase as the first one. The connections are keyed, so you should connect red to red, black to black, and blue to blue. And the ground to the ground. The 3 connections here which are now not connected are used for large transformers where more than 300 amperes is needed. That's for phase 1, 2 and 3.